How wide is the Higgs boson? It may seem like a very silly and unimportant question, but measuring the width of the Higgs could show us where new particles and new physics beyond the standard model are hiding. Discovering the Higgs boson at the Large Hadron Collider is often sold as the end of a journey, the discovery of the final missing puzzle piece of the standard model. However, that characterization couldn't be further from the truth. In fact, we're only at the very beginning of a scientific expedition to understand this key player in our subatomic universe. Having discovered this unique particle, it is vital, in fact it is our obligation as particle physicists, to study its nature, behaviour and interactions in exquisite detail. There is so much more about the Higgs boson and its underlying potential that we do not yet understand. We have only just begun to scratch the surface. The Higgs boson and its underlying potential are linked to the evolution of the universe in the very distant past and the far future. They sit at the very heart of all flavor physics, and the Higgs boson's lack of innate spin may allow it to interact with particles our detectors have never been able to capture. We need to carefully interrogate whether the Higgs boson behaves as the standard model predicts. Does the Higgs boson couple to other standard model particles with strengths that we can precisely predict? Does the Higgs boson couple to itself in line with standard model predictions? And do these couplings align with the form of the Higgs potential outlined by Peter Higgs and his contemporaries 60 years ago? And does the Higgs decay with a rate that we can accurately predict theoretically? There are so many standard model predictions regarding the nature and behaviour of the Higgs that we have simply not yet tested. Indeed, many precision Higgs studies cannot be performed at a messy Hadron-Hadron Collider like the currently operational Large Hadron Collider. The environment of proton-proton collisions is too chaotic and awash with hadronic jets and proton debris, and the energy with which the components of composite protons collide varies from collision to collision. To study the Higgs boson to high precision, particle physicists need to build a high-energy lepton collider, a successor to the Large Electron-Positron Collider. They need a Higgs factory. One measurement that will provide an incredibly powerful searchlight in the hunt for new physics is that of the intrinsic width of the Higgs boson. It's a measurement that will allow us to take an inventory of how the Higgs boson decays and tell us whether it crumbles into more subatomic constituents than we can currently observe or infer. It is one of the primary physics goals of the collider that will follow the LHC. It is a measurement of something incredibly narrow that will have incredibly broad and deep implications. So what is the width of a particle? Well, you could be forgiven for thinking that I'm talking about the physical dimensions of a particle. After all, several experiments have placed stringent constraints on the size of various particles. However, I'm getting at something a little different. The commonly known version of the Heisenberg uncertainty principle tells us that the position and momentum of a particle cannot be known with infinite precision. As the uncertainty on the position of a particle falls, the uncertainty on its momentum rises. As such, we cannot simultaneously measure exactly where something is and where it is heading. A similar relationship applies to energy and time. The Heisenberg uncertainty principle tells us that the energy, and hence via Einstein's famous equation E equals mc squared, the mass of all unstable particles, must have an uncertainty which is inversely proportional to the particle's lifetime. As the lifetime of a particle falls, the uncertainty on its mass rises. This uncertainty is quantified by an unstable particle's natural width, which characterizes the range of masses with which the particle is observed. A particle has a central quoted mass value for sure, but also a spread, an uncertainty in mass. Given that the intrinsic width of a particle is inversely proportional to the lifetime of that particle, the width of a particle tells us its rate of decay. Unstable particles like the Z boson typically decay into a varied set of final state particles. That means that the total width or decay rate of an unstable particle is composed of a series of so-called partial widths, decay rates of that particle to specific final states. So if we can theoretically calculate or experimentally measure the intrinsic width of a particle within the standard model, and then determine the rate at which that particle decays into various final states at a collider, we can check that we've accounted for every final state the particle decays into. If we have, the partial widths should sum to the total widths. We can check that we have fully inventoried every final state particle that an unstable particle decays into. In addition, if we can experimentally measure the intrinsic width of an unstable particle at a collider, and that width turns out to be significantly larger than that theoretically predicted by the standard model, then that unstable particle must be decaying to more final states than are predicted by the standard model. The unstable particle must be decaying to new, beyond standard model particles. New physics must be at play. As such, determining the intrinsic width of an unstable particle is an indirect but incredibly powerful way to shine light on the presence of new physics. So, calculating and measuring the intrinsic width of unstable particles can be incredibly revealing and incredibly insightful. But why is measuring the Higgs boson's natural width so uniquely important? Well, the Higgs boson is itself an incredibly unique particle. It is the only standard model particle with no intrinsic quantum mechanical spin. It is the first and only seemingly elementary scalar particle that we have ever observed. That fact means that it's very easy for the Higgs boson to couple to and decay into many different types of particles. Indeed, it's very possible that the Higgs boson could decay into particles that other particles with spin simply cannot. The Higgs boson is a standard model Sauron. From its lofty tower at the centre of the standard model, it has the ability to see and communicate with all the other standard model particles, and perhaps more besides. As such, the Higgs boson could be decaying into particles that we have not only never seen before, but which we may not currently be able to detect directly at particle colliders. These particles could include hypothetical dark matter particles and other possibilities. Although these particles may interact too feebly to be detectable at a collider, determining the Higgs width would allow us to infer their existence. As such, the Higgs boson is a unique, delicate, and fleeting new probe of the constituents of the subatomic universe. Just as astronomers have moved into the multi-messenger age and now seek to probe the universe at its largest scales using photons, neutrinos, and even gravitational waves, particle physicists now have a new lens for interrogating the universe at its smallest scales. The theoretical total width of the Higgs can be calculated very precisely within the framework of the standard model. In the standard model, the Higgs boson is expected to be very narrow, with a width of 4.1 mega electron volts, 30,000 times smaller than the central mass of the Higgs of approximately 125 giga electron volts. So if we can determine the width of the Higgs boson experimentally, we can compare it with this theoretical value, and if the experimental width of the Higgs is significantly larger than the standard model prediction, that indicates that the Higgs boson decays more frequently than the standard model can facilitate. There must be another partial width contributing to the total width of the Higgs boson. The Higgs boson must decay to final state particles that are not part of the current standard model. The Higgs boson must interact with new particles and via new, beyond standard model physics. So determining the width of the Higgs boson would allow us to inventory its decays. It would allow us to add up all the decay rates of the Higgs to standard model final states, and then see if there's any room for additional decay rates. It would allow us to indirectly determine the presence of new physics and new particles. Although some of you may not have come across this neat quantum mechanical stock-taking trick before, it's actually one that particle physics has used extensively in the past. The width of the Z boson was measured at LEP, the Large Electron Positron Collider, that ran from 1989 to 2000. The standard model predicts that the width of the Z boson is around 2.5 giga electron volts. This total width can be broken up into various partial widths related to the rates of decay of the Z boson to leptons, electrons, muons and taus, as well as quarks and neutrinos. The decays of the Z boson to neutrinos cannot be captured in the detectors of a traditional particle collider, as neutrinos interact so feebly and leave no trace in the material of those detectors. For all intents and purposes, these neutrino decays are invisible. However, by measuring the total width of the Z boson and the rates of Z boson decay to visible final states, physicists were able to constrain how much rate was left for the decay of Z bosons to neutrinos. Then, by assuming that the Z boson couples to neutrinos with a strength identical to that which it couples to electrons, muons and taus, a concept known as lepton universality, they were able to pin down that the Z boson only decays to 3 species of neutrinos, and hence that there are only 3 light neutrinos and 3 generations of standard model leptons. Despite never being able to see the Z boson to neutrino decays, LEP scientists were able to make an incredible statement about the nature of our universe at the smallest scales, all by appealing to the Z boson's intrinsic width. So even if we can't pin down the exact nature of the invisible physics at play, measuring the total width of bosons is an incredibly powerful tool for nailing down whether additional decays above and beyond what we can physically observe are occurring. We need to deploy the same strategy that we did with the Z boson and make sure we have an accurate inventory of all the decays of the Higgs. So if measuring the Higgs boson's width is so important, you might ask, why haven't we done it already at the Large Hadron Collider, the very collider that discovered the Higgs boson more than a decade ago? Unstable particles produced in proton-proton collisions at the LHC, such as the Higgs boson or Z boson, travel a very short distance from where they are produced before rapidly decaying, and we see the decay products streaming through our particle detectors. In order to infer the presence of the mother particle, we can measure the energy, momentum and trajectory of these final state particles, and then trace them back to decay vertices where, by using conservation of energy and momentum, we can infer the mass of the mother particle they must have come from. The width of the Z boson, 2.5 gigaelectronvolts, can be determined to high precision by simply measuring the width of the distribution of masses produced by this reconstruction procedure. And this is exactly what they did at LEP. However, in the case of the Higgs boson, we run into an additional problem. The Higgs boson's lifetime is 600 times longer than that of the Z boson. That means that the decay rate of the Higgs boson is 600 times slower, and its width is 600 times smaller, a tiny 4.1 megaelectronvolts, 30,000 times smaller than the central mass of approximately 125 GeV. Particle physics detectors have finite energy and momentum resolutions. Hence, the reconstructed masses and widths of unstable particles also have a finite experimental resolution. It turns out that the theoretical width of the Higgs boson is much smaller than the resolution of experimental mass measurements. As an example, consider this mass distribution showing events with the Higgs boson decaying to 2 Z bosons. The Higgs boson signal, in red, appears over a range of values, but it's dominated by the precision of the experimental measurement, and not the intrinsic width of the Higgs boson. The best bound on the Higgs width that one could obtain directly from this Higgs peak in data is that the Higgs width is less than 3.4 gigaelectronvolts. That's completely worthless when we're looking to measure deviations relative to a theoretical value roughly 1,000 times smaller. Experimentalists at the LHC have tried developing experimental techniques that allow this energy resolution to be cancelled out. These techniques have managed to produce amazing Higgs width estimates, but estimates that still have an error of roughly 50% and require significant and potentially inaccurate modelling assumptions. However, this level of accuracy is nowhere near what is required going forwards. The goal of the particle physics community is to drive down Higgs width measurements to an uncertainty of less than 1%, an incredible level of precision. But how can we make such an insanely precise measurement of the Higgs width? Well, we need to go beyond the Large Hadron Collider. A precision measurement of the Higgs width is one of the primary goals of a new lepton colliding Higgs factory. whether that be a 100-kilometer future electron-positron circular collider at CERN, the Chinese Circular Electron-Positron Collider, a linear electron-positron collider, or even the ambitious muon collider. During the initial runs of a future Higgs factory, at an energy of around 240 gigaelectronvolts, Higgs bosons will predominantly be created through a process known as Higgs Strahlung. The colliding leptons create a Z boson, which radiates off the desired Higgs boson. However, electron-positron colliders can and will be run at multiple collision energies. As the collision energy is raised, more Higgs bosons are created via the fusion of two W bosons. W fusion. Let's first focus on the lower energy Higgs Strahlung runs, where Higgs boson production is maximised. Electrons and positrons are point-like fundamental particles. That means that all the energy given to a particle is concentrated onto one tiny, indivisible constituent. So when we collide electrons and positrons, we know the energy with which they collide precisely. We cannot say the same at the Large Hadron Collider. The LHC smashes together protons, composite particles made of quarks and gluons. These quarks and gluons are constantly writhing around inside the proton, and when they collide with another quark or gluon in another proton, we can't be certain of their collision energy. Colliding protons is like throwing two bags of potatoes at one another. Sometimes two potatoes inside the bags will collide head-on, sometimes they will just graze off one another. The result is a different collision energy every single time. Since the beam energy at an electron-positron collider can be known with exquisite precision, we can actually reconstruct and count the number of Higgs bosons created by the Higgs Strahlung process in a collider running period, and all without ever looking at the Higgs boson's decay products. This proves to be incredibly important. Let me show you how it's done. The Z boson decays to multiple final states, such as 2 electrons, 2 muons, or 2 taus, well-known percentages of the time. These leptonic final states are extremely clean and easy to identify, and hence easy to count with an approximately 100% efficiency, especially in the clean environment of a lepton collider, free from the messy proton debris and jets created in hadron colliders like the LHC. The final state leptons stream through our detectors, and their trajectory, momentum, and energy can be measured. Since we now have the energies and momenta of the Z boson decay products, and the energies and momenta of the electron and positron in the initial particle collision, we can use conservation of energy and momentum to reconstruct the mass of the particle that must have radiated from the Z boson initially. We call this mass the recoil mass. Sometimes that particle will be a Higgs boson. On other occasions, it might be a Z boson or something else. Since we know from previous measurements of the Z boson at LEP and elsewhere what percentage of Z bosons decay to, for example, 2 muons, we can almost exactly infer how many Z boson and Higgs boson pairs were created during a running period of our lepton collider, all without ever looking at the Higgs boson's decay products. The key point is that at a lepton collider, we can accurately tag and count every time a Higgs boson and Z boson pair is created in the Higgs Strahlung process. This kind of accurate Higgs boson production counting, without having to look at the Higgs boson's decay products, is not possible at the LHC, as we do not know the energy of the colliding proton constituents. To calculate exactly how many Higgs bosons are being created at the LHC, we would need to reconstruct every individual Higgs decay to a vast array of final states individually, and then add them all up. This is simply not possible in the chaotic and messy environment of a hadron collider. Not only do Higgs boson decays get missed in a whirlwind of hadronic jets and proton debris, but what if the Higgs decays to unknown and undetectable final states beyond the standard model? We would never be able to capture these decays, and we'd never even know to look for them. The next step in determining the width of the Higgs is to compare the number of Z boson Higgs boson pairs created by Higgs Strahlung at an electron-positron collider to that we would expect to see based on theoretical calculations. The number of Z boson and Higgs boson pairs generated in a given time depends on the integrated luminosity of the initial electron-positron beams, i.e. how many electrons and positrons streamed along the beams per unit area in a given time, essentially how intense the electron and positron beams are. and how likely these collisions are to create a Z boson Higgs boson pair, the so-called ZH production cross-section. The ZH production cross-section can be predicted very accurately theoretically in the standard model. Therefore, if we can determine the integrated luminosity of our dataset, knowing the number of ZH boson pairs in our dataset, we can get an experimental value of the ZH production cross-section. This experimental production cross-section value can then be compared to the theoretical standard model value. So, how can we calculate the integrated luminosity of our electron-positron collision dataset? The integrated luminosity of the beams at an E+E- collider can be determined with high precision due to the point-like nature of the constituents of the beam and the fact that they interact electromagnetically. When the electrons and positron bunches in a lepton collider fly past one another, they interact electromagnetically by exchanging photons, so-called bar scattering. This scattering deflects the electrons with a well-known angular distribution that can be calculated incredibly precisely theoretically in quantum electrodynamics, possibly the most precise theory ever devised. So by placing electron-detecting luminosity monitoring stations close to the beamline and around points where bunches of electrons and positrons cross, and counting the numbers of electrons scattered at different angles, we can precisely estimate the luminosity of the electron-positron beams. Future lepton colliders like the proposed future circular collider electron-positron phase have proposals to measure this luminosity with an uncertainty of only 1 part in 10,000. This extreme precision will require the luminosity monitors to be placed with a spatial precision of less than 1 micrometer, an incredibly difficult undertaking. Again, such integrated luminosity determination techniques are complicated at the LHC by the composite nature of the colliding photons. The integrated luminosity of the LHC is known only to a precision of 1% at best. With high precision measurements of the number of Z boson Higgs boson pairs and the integrated luminosity in hand, the production cross-section of ZH pairs, sigma ZH, can then be readily calculated to very high precision. But why is calculating the likelihood of producing Z boson Higgs boson pairs so important? Well, this cross-section can be calculated very accurately within the framework of the standard model, and it depends on the coupling strength between the Higgs boson and 2 Z bosons, G, HZZ. Hence, by comparing our experimental value of the ZH production cross-section to the standard model prediction, we can extract and calculate the G-HZZ coupling. This may not seem like very much, but it's the absolute key to measuring the Higgs width with a precision of better than 1%, and it's something only a lepton collider with a well-defined collision energy can do. Now let's finally turn to the decay products of the Higgs bosons in our Z boson Higgs boson pairs. First, consider the case where the Higgs boson decays to a generic final state, XX, which could be 2 Z bosons, 2 electrons, 2 quarks, or some other pair of particles. The rate of production of this final state again depends on the coupling strength between the Higgs and 2 Z bosons, GHZZ, that we just calculated, but now also on the fraction or branching ratio of Higgs bosons that decay to an XX final state specifically. This fraction can be re-expressed as the rate of Higgs boson decays to the XX final state divided by the total decay rate of the Higgs to any final state, the Higgs boson's intrinsic width. The rate of Higgs decays to the XX final state in turn depends on the coupling strength of the Higgs boson to the XX particle pair, GHXX. Now look at what happens if we let the generic XX final state be 2 Z bosons. The number of Z boson Higgs boson pairs in which the Higgs goes on to decay to 2 Z bosons. The rate of this process depends only on GHZZ and the total width of the Higgs. Now look what happens if we take an appropriate ratio between the total number of ZH pairs in our dataset and the number of those pairs which have a Higgs boson that goes on to decay to 2 Z bosons. The dependence of the GHZZ coupling drops out, and we can calculate the total rate of decay of the Higgs, the total width of the Higgs boson. All this just by counting the number of Higgs decays to a specific final state. Since this calculation only depends on highly efficient reconstruction rates at a clean E+E- collider and various well-known kinematic variables and couplings, the Higgs width can be determined to a precision of a few percent. This is already an amazing result, but the accuracy of the width measurement is limited by the fact that very few Higgs bosons decay to 2 Z bosons, only roughly 2 to 3% by best estimates. However, with the GHZZ coupling value in hand, we can go much further. Higgs bosons preferentially decay to bottom quark and W boson pairs. Hence, if we want more statistics for our width measurements, we need to look for cases where the Higgs boson in our ZH pairs decays to these final states. By performing similar calculations to those outlined above for the Higgs decay to 2 Z bosons, we can readily show that the number of ZH pairs in which the Higgs boson goes on to decay to B quark pairs or W boson pairs follows the following equations. We know GHZZ, but how can we get rid of the GHWW and GHBB couplings and isolate the Higgs width with this higher statistics sample? This is where the flexibility of an electron-positron collider comes into its own. If we run the collider at higher energies, around 350 gigaelectronvolts or higher, we can create a large sample of Higgs bosons via W boson fusion. Most of these Higgs bosons again decay to heavy bottom quark pairs, about 60%. The rate at which this process occurs depends on the coupling strength of the Higgs to 2W bosons, GHWW, and the fractional decay rate of Higgs bosons to bottom quark pairs. This fractional rate in turn depends on the coupling strength of the Higgs to 2 bottom quarks, GHBB, and also the intrinsic width of the Higgs. Now look at what happens if we take the number of these events and divide by the products of the numbers from the lower energy run. All the couplings cancel away, apart from the GHZZ coupling that we already know, and we can access and calculate the Higgs width with an extremely high statistics sample, and with a precision significantly better than 1%. Mission accomplished. Simply by counting the numbers of Higgs bosons decaying to different final states, and taking appropriate ratios which cancel out couplings, we can nail the Higgs width with incredible precision. Making this width measurement will be extremely challenging. It will require phenomenal reconstruction efficiencies, excellent beam energy control, and extremely precise knowledge of the running conditions of a future lepton collider. However, if we can do it, we will have a phenomenal inventory of everything the Higgs boson decays into, both known and unknown. And if our experimentally determined Higgs width significantly exceeds the 4.1 megaelectronvolt value dictated by the standard model, we will know that the Higgs talks to particles beyond the standard model, using a language of new physics. The Higgs width measurement is incredibly tough, but incredibly instructive and incredibly revealing. But why, you might ask, do we need to measure the Higgs width to a precision of less than 1%? Why isn't 10% good enough, or the 50% measured by ATLAS and CMS at the Large Hadron Collider? Well, quantum corrections to the Higgs couplings to other standard model particles are at the level of a few percent in the standard model. The quantum nature of the Higgs boson can therefore only be tested if the measurements of its properties are pushed well below the 1% level of precision, to a few parts in 1,000 or better. In addition, if new particles and new physics exist at higher energy scales than we have probed with the Large Hadron Collider, their effects could be observed in corrections to precision observables at the current energy scale. Although we may not be able to directly create and observe new particles with masses of order 10 tera electron volts or higher at current colliders or even the next generation of colliders, These particles can be created virtually in quantum loops and can cause small deviations of Higgs observables from their standard model predicted values at the lower energies at which we are currently working. Interactions between the Higgs boson and other new particles at a higher energy scale, lambda, typically modify the Higgs boson's couplings to standard model particles by less than 5% for an energy scale of 1 tera electron volts. This is why we can practically rule out the presence of supersymmetric particles at the 1 tera electron volt scale. We simply aren't seeing them creating deviations in the standard model predicted properties of the Higgs boson at the current energy levels. The size of the modifications to the Higgs boson's properties typically have a 1 over energy scale squared dependence. Therefore, a significantly below 1% accuracy on a given Higgs measurement would be needed to infer the presence of new particles and new physics at the 10 tera electron volt energy scale, an order of magnitude above the territory currently scoured by the LHC. In short, the more accurately we can measure the characteristics of the Higgs, the further off into the energy frontier we can search for new physics. So we need to be shooting for below percent level precision. In an era where we found no evidence for new physics at the Large Hadron Collider, it is vital that while we probe the behaviour of the Higgs, we also use those studies as a way to assess the energy scale at which physics beyond the standard model may sit. Precision Higgs work is energy frontier exploration. The experimental measurement of the Higgs width will guide particle physics for decades to come. We currently have a fuzzy, blurred, camouflaged image of the Higgs at the Large Hadron Collider. Its true nature is shrouded in a background fuzz of proton debris and hadronic jets. When successively more powerful telescopes take clearer images of the universe around us, the physics of the universe does not change, but our understanding of that physics can be transformed. Having discovered the probe that is the Higgs boson at the Large Hadron Collider, we now have an obligation to zoom in and study Higgs physics in exquisite detail. Despite the best efforts of doomsayers and contrarians in the particle physics science communication space, particle physicists know where they are going next and why. The commonly mooted idea that particle physics is currently in crisis is, to my mind, a bizarre conclusion. The building of future colliders, guided by precision measurements of the Higgs boson, are crucial, have a well-grounded physics case, and boast clear, no-lose deliverables that will drive our knowledge of the universe forward. Of course, there is much discussion within the particle physics community regarding the form a future lepton collider may take. However, almost all agree that the creation of a Higgs factory is a logical step. Any deviations of the behaviour of the Higgs relative to standard model expectations at such a Higgs factory will provide signposts for where new physics and new particles beyond the standard model may be hiding. It is our job as particle physicists to study this fascinating new particle and illuminate those signposts. We are not simply seeking hypothetical dark matter and SUSY particles dreamt up in the minds of theorists, as certain online influencers might contend. We have clear goals, an obvious and far-reaching physics case, and definite no-lose physics deliverables. One such key no-lose deliverable is a measurement of the Higgs boson's total width, a key first milestone in particle physics' next journey. It's a measurement that gives us indirect access to everything the Higgs boson sees and tells us where to go next. As narrow as the intrinsic Higgs width may be, its implications are incredibly broad and incredibly deep. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.